In this video, we will start talking about comparing distribution. In this new example, we will using the example about jury selection in Alameda County. In the jury selection process, we talked about from the last two lectures. So the jury panels, when we choose the jury panel, we have few steps. So the first thing, of course, we will have all the eligible jurors from the county. So then you list of the eligible residents. So then we will have the random selection and the fair selection. So we have our jury panel. Of course, the actual juror will be according to some final selection from the jury panel. So the most important thing we should know is from selection 197 for the California Code of Civil Procedure say, all persons selected from the jury service should be selected at random. So that's important why we can use our data science to do the simulation, because all we care about is the random sample. So that will be selected at random from the source or source inclusive of representative cross-section of the population of the area served by the county. So that's very important from our eligible juror, no matter where they are and what the background they have. They all have the random selection being fairly selected. The most important thing in this example is, from our previous two examples, we can see we only have two categorical data. The data consists two category. So when we even say two category, honestly, we only have one category, because the other category is a complementary from the first category. So for example, we say that the juror is from our robbers example. So that's from the black people or non-black. So then from our genetic example, then we just say that 75% or not 75%. So that's a complementary from each other. In the new example here, we will show you is we are not only have one category, not only two category, we have 5 category. So how can we do the simulation and assessing the model? So that's the most important thing we want to see here. So that's why we were thinking about the statistic thing is, since we have more than 2 categories, so when we want to choose a statistic to represent our simulation, be meaningful to select that statistic from our data set. Sometimes, we have multiple categories. So some category, maybe they are underestimate, or the other one is the result is too high. No matter what, we need to take consideration of all the differences from all the category we included. So on the other hand, we need to consider of all differences from a more complicated data set. Then from them, we still need to choose only one statistic to do the simulation. So that means we need to only summarize for the one single value that can represent our data. So that we will introduce you in this example. We have 5 different categories. But before we start talking about the new statistic, let's see our data set first. So let's see our example. Like earlier we say, we have the new example is from the Alameda County jury panel data set. So that's why you can see in this data set, we have different ethnicity. We have 5 different categories. So in each one, we have their percentage about their eligible. Then we have our panel result. Also, that's our observed data. Okay, so then you can see the table look like this. Okay, so before we see the statistic, let's see the bar chart to show you how differences about our observed data. So what the percent from the real panels and from the eligible. Okay, so some of that are very close by, but some of that maybe one, you see like Asian here, we have, I think the panel is much higher than the eligible. But like Black or Latino, they are underrepresented. Okay, so here we need to think about when we want to really compare our simulation result with the panel. Okay, how should we consider all the category, the differences from the expectation data with our real eligible data from all different categories? So before, when we have like the our genetic example, at least you see we only like say 75%, or our jewelry example, we only have either the black jewel or non-black. So that's very easy to just calculate the difference. But here we have 5 differences. Okay, so how can we really use one statistic to represent 5 different categories? So back to our slides. So we need to see the new statistic we are looking for, the distance between distribution. We need to include all the 5 different categories. So that means the people on the panels of multiple ethnicities, we all need to be included. So the distribution for that, of course, that's categorical data. So before, if we only have 2 categorical data, we only have 1 distance, but now we have 2 distance. And not 2 distance, we have 5 distance we need to consider. So from this one, we want to introduce you the total variation distance. So you have more than 1 distance need to consider. So every distance have a computational recipe. When we need to consider all of that, for each category, we need to have the difference between the difference in proportion between 2 distribution. So then we need to do for each category. So to find the distance, of course, we need to find the absolute value. So we can include either they are less than or more than. We won't have the negative and positive value to cancel each other. So we take the absolute value of each distance. Then we add them together and divide by 2. So here divide by 2, you don't need to think too much. You can, even we have 5 categories and we just divide by 2. It just kind of from the statistic point of view, we make the difference a little small, but it doesn't mean that by 2 has the real meaning there. Okay, so that's why if we go back to see our example, for all the category, we need to do the simulation. Then we need to subtract each other from our eligible ratio for each category. Okay, so then we can go back to see our example. Okay, for example here, like from our observed data, we need to use each one to find the differences between the panels and the eligible ratio. Then we all add together. So according to our TVD calculation, so then we will add together and divide by 2. So let's see how to do our model simulation. So of course, under our model, we assume all the data, the juror being selected fairly randomly. And also we need to mention about that in our random draw, we have 1,423 juror. So that's what we will use for our sample proportional function. So even we have more than 1 category, so the same thing, that's make our array. So this array we call model. So that's have the percentage for each category, their ratio, the eligible juror ratio. So then when we want to do the simulation, that will be the same, even we have more than two categories, we're still using the sample proportions. So you provide your sample size, and the array contain all the ratio for all categories. So then when you run, okay, here I didn't run this one. Okay, so then each time you run the same thing, right? So that's they will really get sample size 1423. So then they simulate, then we got the different category, what their percentage. Okay, so the same thing, of course, every time you run, the result will be different. So then here we just add this one to our original table. Okay, so the panel is our observed data. Simulated is every time we run the simulation. So of course, in order to test assessing our model, we need to do the simulation with a large amount of time. Okay, so then we will use our new statistic value, the total variation distance, to compare the simulation result and the observed data. Okay, so that's the bar chart. Of course, you see the simulation is not good enough. This one just like a one-time result. Okay, so then how we really do our simulation? So then since we have our new statistic, so then that's prepare for our simulation. So that's earlier we call, right? That's distance between distributions. So we have the distance from each category, then we add together, then divide by 2. So the first thing we just show you on this one, that's using our observed data first, then our eligible ratio. So then we see the difference. So this one, we can just have one additional column. So then you see we just subtract each other. Okay, so then that's why you can see each difference. Each difference, they are either positive or negative. So that's why we say we don't want they cancel each other. So then we need to find the absolute value. So our total variation distance, that creates our function for that. So this function, you have two values. Each distribution doesn't matter. So which one is your simulation, which one is your eligible ratio, that doesn't matter, because we will take the absolute value, then we take the sum, then we divide by 2. Okay, so then here, after we have that, so that's why you will see here we run again for our eligible ratio with our observed data, the panels. So then you will get, that's about 0.14. 0.14. So far, you don't know how this data look like. So we need to compare that with our simulation. But here we just have the data on the observed data calculate first. So now we can prepare for our simulation. So our simulation, like earlier we said, we need to do 1423 times. So every time we got the result from this, your 1423, so we pass in the model array. So then we will get our result, each simulation, then on different category, their percentage. So the same thing, right? We pass into our TVD function. So then we can get our total variation distance. But the same thing you see here, just run one time. Run one simulation one time. So in order to get our empirical distribution, so we need to run this simulation big times. So this one we do a lot, right? Okay, so we will run the simulation 10,000 times. Okay, so every time we need to call this one. So since we need to run this one, we make that as a function. So we have simulated TVD. So then we just run our simulation one time and compare with our model data. So then we got 1 hour TVD. So we need to do this TVD 10,000 times. So the first thing, we create an empty array. So then we do 10,000 times. So each time we just run the TVD, then we add to our TVD array. Okay. So then we finish that. So of course, we need to see our histogram. So that's why according to our TVD results, we put in a table. So that's the histogram. Okay, so let's create a histogram first. Then we will discuss in the next video about our compared to our observed data.